It's my pleasure to introduce Sherif. I'm not going to try to pronounce the last name. Sherif is the Associate Director of the Distributed Analytics and Security Institute and an Associate Professor with the Electrical and Computer Engineering Department at Mississippi State University. His areas of expertise is computer engineering, a specific interest in cyber-physical systems, cybersecurity, autonomous computing, real-time systems, modeling and analysis, discrete event and hybrid systems, and the list goes on. And after this morning seminar, we're all a little bit educated about many aspects of and challenges of cyber-physical systems. He's received his PhD from the University of Toronto, and after that has worked with Vanderbilt University and Rockwell Scientific Company. He's established collaboratively the first NSF-I UCRC Center at the Mississippi State University. Has chaired several conferences, has over 120 publications, and is also the recipient of the State Pride Faculty Award, the Badley College of Engineering Hearing Faculty Excellence Award, and the 2016 Faculty Research Award from the Badley College of Engineering at MSU. Thank you very much for coming. I have one last comment outside of what you have read already in his CV. Is for many years I'm trying to understand how one can be very successful in system engineering. I think it's the first time that I see someone very successful focusing on traditional cyber-physical systems engineering, so that's very impressive. Thank you very much for being here, and I look forward to your lecture.
So actually I'm compressing two presentations together today. So I'll go a little bit faster than normal.
You need to connect something.
To log in. Yes.
You need to
swap from, yeah, that's the computer.
Yeah. Just
push the laptop. HDMI. So I was a bit confused about which, so I actually did this in the morning, so I'm going to repeat. This is supposed to be the seminar that I did in the morning, so I'm going to repeat part of that and then talk about future direction at the end. So again, we have here a problem with cyber-physical system. In the past, we deal with standalone systems that are domain-specific, isolated, restricted in operation conditions with very limited flexibility. Currently, we are dealing with the large interconnected network of components with various degrees of complexity, communications, interactions, and they are dealing with a large different set of domains of application, including manufacturing, aviation, scientific, power grid, etc. Systems are getting too complex to the extent that any kind of previous analysis, design, and control that was applicable to past systems is not applicable in any way to the current form of cyber-physical system. So for this system to work, we need to figure out a different way to deal with them that can solve the industry problem that is out of techniques that can deal with the system manually, how to deal with integration with new technology, ordinary people, how to make it more usable for ordinary people, how more flexible for their based on their knowledge about the system, and easy to access. From the research and engineering perspective, we need to deal with scalability and complexity problems of these systems and address different kind of quality of service and reliability aspect of their operations. So one proposed solution for dealing with all these problems is to make the system autonomous in a sense that they will be able to self-manage themselves with little intervention or no intervention from human operators. The approach I took in most of my research is to take a self-managing system approach in which the system is able to sense its operation environment, model its behavior in that environment, and take action to change its own behavior in reaction to this environment. So in a sense, they are trying to play a game with the environment. The environment push some kind of new conditions in the system, and the system will reply back by adjusting its own parameters so that it will adapt effectively to these conditions, new conditions, in a way that allow to maintain a high level of performance and keep the system accessible to the system users. There are four main branches that altogether compose a self-managing system. One being a self-configured, able to adapt to changing environments, self-optimizing that can optimize resource consumption and reduce the operation cost. Robustness and resiliency falls under the self-healing property in which the system is able to discover and diagnose and act to prevent disruptions that are caused by failures. And last but not least is the self-protection capability in which the system is able to detect the early signs of attack and manage its resources and sensitive aspect and critical aspect in a way that maintains functionality and keep the system secure and the data safe. My research work in self-managing system has three main directions. The first one is to develop models, operational models, and specification for the system. These, to a large extent, are formal mathematical models that the selection of the model is usually dependent on the system dynamics and the problem that we're dealing with. Can range from a simple finite state machine all the way to a hybrid automata and hybrid system description. And the model not only used for analysis, but can also use for simulations and can be used for controller synthesis. And the next part is actually building the management structure using control and feedback control techniques. I dealt with a centralized control architecture for small-scale systems and a distributed control architecture for large-scale systems. And to make this system, the result of these two directions applicable in real life, we need to produce the tools and the environment that can be used easily by the engineers and the users of these tools in order to be applicable or utilized in real life scenarios. This shows the architecture of a control framework for self-management, particularly in cyber-physical system context. Very high level, but it shows the main components. That the cyber-physical system is described by a system model, and the system model is driven by two forms of action. One of them is coming from the environment, in which I cannot control, but I can predict, and we use an estimation filter to predict. And the other one is a controllable input that can be used to tweak the system behavior and adjust its properties. From that, this information about the state and future state will go to a performance optimizer that uses the system specification constraints to compute the best option or the best control input to take in order to optimize the system performance. Because the systems are usually complex and not fully described in a precise way, the initial system model might not be accurate, and we need some kind of a form of model learning to compensate for the inaccuracy and learn from the model as it progresses throughout its operation cycle. System modeling, for most part, we used, and it was my collaborator, we use the form of hybrid system model in which the control set is purely finite. Described by this discrete time equation, in which the next state is a function of the current state, the input, control input u, and omega is the environment input, which again we cannot control, but can estimate and predict it for the future with certain accuracy. This model can be and have been used in many applications, including enterprise systems, critical infrastructures, power system, power grid, communication systems, and even in cybersecurity. We were able to represent the system with great accuracy, actually, in many situations, using this formulation. The advantage of using a discrete set of input is coming later on as I discuss the stability problem. Stability is very hard to verify for hybrid system. There is no like Lyapunov kind of stability for this side of system in general, but we can actually, for this particular restricted set of system, formulate a stability as a feasibility problem, set attraction problem. I'm going to talk about it soon. Again, because we're dealing with complex system, we're dealing with most of this stuff is directed toward practical applications. So we're looking for practical way to model the system, practical way to control the system without compromising on the on the techniques being quite formalized and quite rigorous in terms of development, and has the tools to verify that it works. For that, we use the limited locate control, which is a version of model predictive control in which we foresee or forecast the future behavior of the system up to a certain depth and select the path that optimizes this behavior with respect to certain cost or utility function while satisfying the constraints on the system. Then we take the first step along the path and move the system toward the next state using the step, and then repeat this process by generating a new set of states, forming a tree of all possible actions, and repeat the computation of the best step to take. The objective here is to reach the desired region or the optimal region, whatever it is, either specified by the utility function or by a set point formulation of that function. One application of that was funded by the ONR. We have been working that for about 8 years. And the objective here is to build a power management system for their destroyer fleet. The new ship, DDG 1000, is an all-electric ship. And here shows a very simplified schematic of the shipboard power system, where it's divided into 4 zonal loads, driven by 4 generators, 2 main generators and 2 auxiliary generators. The system is feeding a proportional model that drives the ship, which is taking a heavy part of the load, plus the auxiliary load across the ship, plus a very important part is a pulse load, which is feeding the weapons in the ship. And the system is moving through different modes of operations, starting from a cruising mode to battle mode, and the requirements in terms of load priorities can change depending on the situation. So propulsion load is vital when the system is in a cruising situation. Motor load is semi-vital. Static loads that are used by lightning and other component of the system, dependent on the static load, can be either non-vital or semi-vital. We formulated this as a control problem with different objectives that need to be satisfied, including maintaining the voltage at a certain level throughout the bus, keeping the distribution of load balanced among the generators, maintain the reliability of the system by not switching on and off the different control aspect and relays and switch into the system, and keep the system with high survivability at various operation conditions. Relative factors include the cost of connection, disconnection of certain loads, energy balance, capacity of generators, priority levels of loads, as shown here, system bus voltage response. Again, this is formulated as a control problem. We develop a centralized system for that is using a simplified model of the system with 37 states. The actual system has hundreds of states, and we are working in the next step to apply what we developed earlier in a distributed form to the actual system model.
I have a quick question.
Yes.
Do you control the 37 states at this point of time together?
Yeah.
Okay.
Yeah, it's a whole system. So it's a centralized system in this case.
And how many can you measure out of those 37 states?
In this case, all of them are measurable.
Oh.
Yeah. These states are mostly current and voltage, taken at different instance through measurement units. And also we take the phasor measurements using the PMUs. And we take the different, some other stuff like the rotation angle, rotation speed of the proportional motor, and the what we call the droop gain factor of the generators. These are all collected and used for estimating the system.
And how many inputs do you have?
For that, we have 6 inputs corresponding to the share of loads and the droop gain factor, which is used to stabilize the voltage.
And what control system?
The MPC, the one that I described, model predictive control. We use actually 2 forms of MPC. One is a continuous MPC that use the assume that the input is continuous. Another one is discretized using the search tree I described there.
So how do you implement a continuous MPC?
It's using fmincon in this case with simulink, so an optimization function.
I know, but you can't implement a continuous time.
The model?
No, the controller.
The controller, it's an MPC, model predictive.
Yeah, but it can't be continuous, right? You measure at some point and then you...
Yeah, you still have to sample.
Yeah, that's what I meant. Yeah.
So you need to sample the situation.
Okay.
The system itself, what I mean by continuous is the input is continuous, but the system itself is sampled.
Yeah.
Whether it's using a continuous input or a discretized input. So we always sample the system. We experiment with this in a discrete time, discrete input and a continuous input. We dealt with it as centralized and decentralized distributed control, and we got several papers out of that. We actually developed also a set of tools that can be used for synthesizing and deploying the controller in the actual chip whenever is needed. Another approach is for the signal detection system. The problem here is to deal with the trade-off between detection of signal accuracy, the accuracy of detection, and the real-time property of the system, which is what we call the quality of service. Here we're collecting signals from the field. Some of them are PSK, different modulated form of signals. The signal classifiers try to define the kind of signal, whether it's of interest or not. That's a DARPA-funded project collecting signals in the battlefield to try to classify them and figure out which one is relevant to the operation being taken and filter out the noise. So classification at the initial stage will require some limited, not heavy processing power, but require more real time is more emphasized in this case. We need to get as much signal classified as possible. Once we narrow down the selection, we go another loop in which these signals are going through a more precise loop for accurately classifying. This can be modeled as a physical system with a Q level as one of the states, processing speed as another state, and we get and sometimes we need to drop some of the signals to compensate for lengthy Q here. So again, we take this into consideration as part of the control system. We experiment with actual field data that comes out in the experiment, and we show that the controller was actually quite effective in selecting different control action to maximize the overall performance of the system, which to maximize the response time, minimize the response time, the latency as short as possible, and maximize the accuracy of detection.
Question?
Yes.
Is there a way to measure which controller is better than the other in terms of, are there metrics that we can evaluate two controllers over such framework?
Yeah, well, the metric here is how close they are to the optimal point. And the optimal point is very difficult to obtain in a nonlinear hybrid system. It's not really easy to find out what is the optimal point. So as with many other systems, our baseline is to look for a system in which, because the critical factor here is the fluctuation in the environment, the arrival rate of the signal. So we have to predict it. This needs to be predicted to take the risk control action. Now, if we assume that we have an oracle that can predict with zero error, then this can count for us as the best case scenario. Because no controller can exceed it. If you know everything about the signal and can prepare for it, it's like seeing your opponent and know exactly what he's going to do.
Yeah.
So you can do the best action possible. So that for us is a baseline. But another baseline that can be taken in some situation is to compute the optimal point, which is very difficult for most of the scenarios, and see how close you are from that. And again, that's can vary between one system to the other, because some systems there's no way to compute it. It's just beyond the computation capability. And some others, it's possible, and you can use that for measuring the control performance.
And what is the timeline of these response times? As in, are they in milliseconds or are they in seconds?
Depending on the system. Like in here, for example, we are dealing with a sample time every 30 seconds. Every 30 seconds, half a minute. And in other situations, we can deal with milliseconds, nanoseconds, picoseconds, depending on the situation and the system dynamics. Stability is a very important aspect of that. Although we are dealing with practical applications, very important to make sure that we have some kind of guarantee that the system will work in this practical application. So we formulate the stability of this problem as a set attraction problem, where we're trying to attract the system to the set point exists here, and figuring out the hypersphere that will contain the controller and around this set point. This can be formulated and is shown in several papers that we have published can be formulated as a nonlinear programming, which can be solved very easily with MATLAB to compute the minimum containable region, which is the ball BR of XS, which is specific to the system dynamic. So given the dynamic and the requirement of one-step controller, we can actually compute the radius, and that can give us some kind of quality of service guarantee and how close we can get to the set point and maintain within this area. Another application for the same technique in a different domain is the enterprise system application, which we are trying to regulate the traffic to the system. It's a multi-tier system. We have different tiers distributing the loads coming from the users to these tiers. The control action is the load share for each of these virtual machines, also the frequency of each processor within the virtual machines, the state of the virtual machine being on and off, some of that, and the putting the virtual machine in an active or a passive replica for reliability. So that has been implemented in a real life scenarios in which we have 3 services offered by the system. Some kind of a cloud environment where you actually host your service in a cloud, and you try to optimize the cloud environment for these different services. We experiment with DVD store, what's called the stock exchange, and a bulletin board scenarios, kind of typical benchmarking for enterprise system. And with the controller, we found that the system, we show that the system can save 26% of the power, which translates actually to millions of dollars for big data centers, while very small violation of the service level agreement, which is defined as the response time of the system. Another domain is the NASA Advanced Life Support System. That was a NASA funded project for a hypothetical mission, 90-day mission to the moon. They actually have built the system. It's in Johnson Space Center, and we went there and talked to the engineers. The system consists of a water recovery system to recover the water, recycle the water generated throughout the operation cycle, air revitalization that exchange CO2, O2 between the crew and the crops that is used for food, crew chamber in which the crew are set to do most of their activities, and a food production area, plus the power generation and the thermal control systems. It's a very complex system, took significant size, number of iterations with the engineers to model, start with the schematic of the system. As much as possible, the parts of the system that we have knowledge about, we model that. The others, we have to go back to the engineer, model them, translate that into a hybrid bone graph for both control purpose as well as failure diagnosis, because hybrid bone graph is not only for dynamics, but also can capture causality. Take this information and translate same information to a high fidelity simulation system, not just based on hybrid bond graph, but based on the description of these systems that we cannot capture directly as a hybrid bond graph, but we were able to get a more high fidelity simulation, capturing most of the dynamics of the hybrid bond graph, and then compare the simulated data with the actual data coming from the system, which we have access to, iterate over that until we reach a satisfactory level of closure between the two. So it's showing the water recovery system in which the feed tank is going to biological water processing to remove bacteria and other hazardous material from the water, and goes through reverse osmosis and air evaporation systems. Reverse osmosis will recover 85% of the water. Air evaporation takes 15%, goes to post-processing again for cleaning, further cleaning of the water, and the result will go to portable tank water, which can be used by the crew and the crops. So the problem here is how to maximize the water flow or keep it at a certain level, and maximize the quality of the water, never below certain levels, so that it keep the crew healthy, and also to reduce the waste as much as possible in the process. To show the again, the control architecture for the overall system. It's a 3-year project, and it's a multi-level control architecture. We have global controller. We distribute the objective over different level of controller. The global controller, the main objective is to keep the crew alive, to keep a certain minimum level of oxygen and water and food resources for the crew. Then we have controllers for each one of these modules of the system, one for air revitalization system, one for the crew controller, and one for the water recovery system. And even the air revitalization system will have different local controller LC here that is connected to some of the modules of these that are exchanging information. So this one is trying to maximize the overall efficiency of the system in terms of producing O2 and absorbing CO2, while the local controller is dealing with the efficiency of individual parts of the system. The same here for the water recovery system. We have air evaporation system that has its own controller, reverse osmosis that has its own local controller. Both are managed by the water recovery system controller to, again, overall maximize the performance of this in terms of quality of water, flow, and level of water in the reserve tanks. Now, in order to get this actually usable for the system, we need to do some tool development here that will, as much as possible, hide the complexity and technical details from the actual user and present them with information that can be translated into the formal models and techniques that we develop. So basically, we develop a domain of knowledge in which the main components of the system can be connected together and initialized to their nominal values. We also can have a way to formulate the specification for the system as part of this description. We take this information because we have already templates for each one of them that specify its behavior in a class template format. So we can, using the data coming from the user, we can actually initialize these with real data and connect the classes together to form an overall system that can be used for deployment and actual operation. The base architecture here, or the base tool here, is a GME tool that was developed at Vanderbilt, and I was working there for 6 years, heavily utilizing this tool for many projects. And it's a meta-modeling environment in which you define the meta-model as a class diagram, UML class diagram, identifying the different classes of the system and how they are connected together, what kind of attributes they have. These classes will show as components that the user can drag and connect using input and output ports and specify using attributes and parameter windows in the tool. One application here is UEV tracking, surveillance and target tracking. And here the system goes between a surveillance mode in which we try to survey a whole area, big area. Here we try to maximize the area that I can survey. That can be at the expense of the quality of the information coming from that. In the target acquisition and the engagement mode, we try to look locally into some of the points within the surveillance area for more accurate. Here we are emphasizing on more accuracy rather than the area of surveillance. And also we need to deal with better damage assessment, in which some of the elements of the fleet is failing or hit or actually missed from the fleet. So how we can reconfigure the whole system to maintain the overall functionality. So, these are exchanging information between each other, as well as with the command center, which is taking the information coming from the fleet and analyzing it and send the commands back to the UCAVs for further action if the target is of interest. So I'm focusing here not on the control problem, but the tool that has been developed here. This is the UAV application domain meta model. I defined all possible classes and elements in this domain, how they are interconnected together. And they can vary in aspects. So this class diagram can deal with some aspect of the system, another class can deal with another aspect. For example, in the NASA Advanced Life Support System, one aspect is dealing with the hydraulic functionality of the water recovery system. Another one deal with the electric components and how they are modeled in the system. So a system can have multi-aspect, and all of these need to be captured and connected using meta models. From that, I can have templates for every part of the system, which I can drag from here and connect together to form an actual system structure that I can model and simulate and analyze. Show linear an actual system that has been specified using the tool. You can see if this is the component window where you can drag and put here and specify in more details. Each one of these are clickable. You can click on it to go into the second level of detail where you can provide more details about the internals of each components and all the way until you get the main parameters and how they are connected together as part of the system. This is a multi-level structure. We have a local resource manager that is attached to each one of these UEVs and UCAVs, and there's a global system-level resource manager, SRM, that is dealing with overall system optimization. You can here specify the different requirement of the system and the trade-off within the rules. And the surveillance, for example, you adjust the rate of image resolution followed by the size. Target tracking, the rates, you adjust the rate and allow cropping if necessary. Better damage assessment, you adjust rate size and allow tidying of image as needed.
So, how do you build that? Inside out, or so you start from the high level of abstraction when you develop, I guess, not when you use it.
Yeah.
So you start from just the high level requirements and then slowly you develop the.
Yeah. Again, it depends on the system. Sometimes you go bottom up, sometimes you go from top down. In this, like for example, in the advanced life support system, it goes always from top down because we have a clear set of high priority objectives. So we have the top level is that, for example, to keep the overall system, the main function is to keep the crew alive. Then we go to another level at the component level. What the objective of each component is to maximize its efficiency, the flow in the output flow of that system. And then you go to individual component of that and how to make sure that this component is effective with respect to, again, being part of the cycle within the component. So there's different level. You can start from the top level, need to satisfy this first and then go down, given a constraint. The top level, for example, tell me that the water tank should always have this minimum amount of water, no matter what. The oxygen tank should have this minimum amount for a given remaining duration of the mission. Now, within that constraint, I go down. Okay, now I know what is my limit. So can I optimize within that? I have the flexibilities going above, but only to this level. So what can I do after that? So it's going like one step at a time. Satisfy one constraint, top level constraint, go next and see what will be the most important part, all the way to the low level constraint, for example, that I want to keep some remaining content in this tanks for future mission, which if I don't satisfy, it's not a big deal.
So do you have dynamics at some point? Time as
time scale is a big deal here because each controller has its own time dynamics. And the local components, for example, the reverse osmosis component will have time dynamics that is measured in seconds. While for the overall water recovery system, I'm measuring in terms of hours because it doesn't make sense to measure in seconds here. It's a very slow system overall. And then the overall system I'm measuring with respect to days. So we have an operation cycle in days, and I want to optimize with respect to that. And then the final top level is dealing with the whole mission from the start to the end of the 90 days. That's one time cycle that I need to optimize with respect to.
So how do you
define that?
Hierarchy of time?
Well, again, that's based off the information we get from the system engineers and designer and depend on the system dynamics. So there's no generic or general rule that I can apply here. It's a system dependent and situation dependent. But yeah, we have to deal with different levels of priorities, different levels of dynamics, and we have to adjust the controller structure accordingly.
So how easy is it to change the model for this particular mission to have, say, more number of UAVs, and in this case you have 5 UAVs, right? So what if I add 5 more, and what if I add 3 more faster aircraft, and how easy are these models to change?
Very easy. That's actually one of the advantages of this approach is that if I want to add one more UAV, I'll just drag it and put it, connect it to the command center, and I have because the composition rule is the same. Whether we put 4 or 5, it's the same composition rules. They need to communicate somehow in some mechanism with the command center and take feedback from the other UAVs. So as long as the composition rule is defined, I can take out components and remove put components and compose a system again, interpret it, and I should get a new system description reflecting the changes. That's one of the main advantages of that, is that I can change the model, generate a new code, a new simulation engine, for example, if I want to simulate, instead of 5 UAVs, I simulate 10 UAVs, and build the control structure for 10 UAVs in the same way and the same steps that I'm dealing with 5.
So if I raise that number to 500, what is the constraint?
Well, it's a computation time. If the controller is not distributed, then the scalability will kick in sometime, and then you'll not be able to cope with that, especially in the verification problem that I will talk about later. Here, again, the multi-level control, I'm going to just one dealing with overall system resource management, and then dealing with the local resource managers at lower level to make every UAV effective with respect to the domain or range of parameters that are provided by the system level resource manager. One of the other benefits of this approach is that I can automatically generate code and synthesize a controller, and that's all done in the background. And even I can change the language that this is produced. This is shown as C++. I can produce one in Java or Python as needed by the platform. I can even generate code for MATLAB for simulation. I can generate files for verification using LoopApp. All of these, dependent on the aspect and dependent on the way the system is described, can be used. The same description can be used for different paths, as long as I specify the corresponding template for that path. I'm going to talk first about the verification aspect here. For model-based design, verification is very essential. Here again, we start with a domain-specific model that captures the essential of the system's main components and how they are interacting with each other, from which we deal with, we make a semantic mapping to an analysis model, whatever it is, can be cryptic structure or timed automata or hybrid system, whatever is needed for the analysis, which can be feeding model checker or simulator. Simulator is used to check that the code generator from the domain-specific model is accurate with respect to the analysis, and they have pretty much the same behavior. One application of this work is for the Boeing both-stroke platform, in which we have a lot of tasks running in the avionic mission system, including weapon targeting system, airframe navigation, sensor control, GPS, different kind of filters, heads-up display, autopilot. These are tasks within the system, and some tasks are getting events from some of the sensors, which usually publisher. They send that an event channel, and the subscriber tasks will take these events. So a navigation system, for example, will receive an event from the GPS about the coordinate of the aircraft. And then the navigation will take that and show that in the display. So there is connection between these tasks. These are software tasks that have a worst-case execution time, deadline, and allocation to processor constraints. What we need to verify here in this project is the schedulability of this. If I have certain properties of these tasks in terms of deadline, worst execution time, and allocation to different processors, how can I put these and verify that the system is scheduled, meaning that every task will meet its own deadline? So we built a tool for doing that. One is in which we can capture the system dynamic using the domain-specific modeling language, ESMR. And then we have transformation that is using the great graph transformation tool that was developed at Vanderbilt also, and part of GME, to translate that into a formal model, capturing the same dynamics, which in this case is the timed automata, and then generate the timed automata file that can be model checked by some of the model check tool. In this case was Google. Showing here an instance in which we have a timer is triggering INS and GPS modules. They feed the airframe module and then they go to the display. Each one of these modules has a software task. It has again starting time, ending deadline, worst case execution time, best case execution time in some situations, and how they are related to other tasks, how they bind them together. This is the description. Translate to this structure using GME, which captured again the main modules here, the channels connecting between them, and the timer that is triggering them. Using model transformation, I take this information, translate it to the corresponding machine. For example, this is the one that is correspond to the display task. That's the ESML modeling for the some instance of the bolt stroke application, whose 4 components are connected together through channels and triggered by timers. This is the actual scenario that we run, which we have several processors. Each one of these processors are allocated with some of the tasks. So GPS is contained in airframe, are contained in CPU1, pilot waypoints and routes and are connected to CPU2. Each one has a priority. Each one has because this is priority-driven scheduling, each one has a worst-case execution time and a deadline. This information is what we take to translate it later into a timed automata that carry out all this information in terms of deadline, triggering conditions, and worst-case execution time as part of that. And we translate the problem into a deadlock problem. So that the system, if it didn't meet the deadline for whatever reason, it will be trapped in this state, which can be checked formally as a deadlock property. So if the system is not deadlocked, then it means that all the tasks will meet their deadline. Any task will not meet the deadline, will be trapped here, and the system will be deadlocked. I'm going to go through this fast. Another application area is the ARA mobile platform, which was a very ambitious project that started by Google and was contracted to Metamorph in Nashville. We're trying to verify the interconnection between different parts of a mobile platform. The objective here is to build a modulus mobile platform in which we can remove some parts of the mobile phone and replace it, so we can change the camera or the screen and keep the other parts of the system. Challenge it if you are moving one part and replacing by another, how we make sure that the system will remain functional after that. There is no kind of blocking conditions or whether live lock or deadlock that can happen because of that. So we took every part of the system, model it. Many of these parts are already modeled as a system C, so we didn't have to go through the modeling. We just take the system C as part of the description, use some translation tool that translate that into abstract syntax tree, and that is just generic description of a programming system. Take another tool which is developed in Germany that translate the AST to a UPAL model and use that for GME. The GME was very useful in order to chain all these tools. So the user of this tool does not have to know about all of this. They get the description of the system, automatically translated for them into system C design. At the end, it will generate a UPAL model, fed automatically to the UPAL model, checking, verify the property. All what the user say is, does it work or not? And if it doesn't work, it will point out to a scenario in which the system is not satisfying the required property. Yeah.
So how do you handle the heterogeneity of these? As in, there are multiple modules, and some of them having DSPs, as in the camera modules. For the interface is widely different for each of the modules.
Yeah.
And how do you handle that in this particular?
Oh, well, each module is developed independently. So the camera module have its own components, for example. and have its own software tasks associated with that, and have its own bridge connecting it with the other part of the system. So we take that and we put a generic kind of description of it, which can be specified further or change it as needed if a new camera module came out. But we put the main aspect of the camera module as part of the model. All the user need to do is either change it as needed, attribute it with the attributes, and then connect it to the other module. Let's say that you want to have two cameras, not one. And you can put two cameras as part of the system, connect them to the main bridge and main bus of the system, and they should be able to exchange information with other system components and other software application runners. Now, for future plans, I want to carry out this work and extend it to allow self-healing capabilities of the system. Already some preliminary work on that. My vision is to have a system that not only self-optimizing and self-configuring, but a system that can deal with every kind of aspect of adaptation, including self-healing and self-protecting. And they are put all together under one framework and will be put in a generic way that can be applied to a variety of systems. What I need to do is to have a controller modules that can be attached to the system components and through a predefined sequence of simulation and in addition to some generic models of common modules in these systems, I'll be able to compose that and make it very easy to build a control structure that deal with all aspects of self-management system. Self-healing, the main aspect of it is the integration with the diagnosis module, fault diagnosis module that will be able to diagnose the fault, and a prognosis module that will be able to predict the propagation of the fault. And actually, I worked on a couple of projects on developing diagnosis and prognosis modules, both for discrete time and continuous time behavior. Now I'm trying to connect that, and there is some already preliminary work on that work for enterprise system, but I want to extend that more to general cyber physical systems, allowing both modules, discrete and continuous diagnosis module, to work together, fuse the data, feed that to the controller to identify the impact on the system and run some kind of risk analysis so that it will eventually bring the system to a stable state in which it's still functional, still productive, and with the minimum damage. For that, we'll have to have some kind of redundancy in the system, and part of the control action is to manage the replica of these components. We need to have capabilities to move things around so that if some part of the system is destroyed or reduced efficiency, then I can move between these components together. This shows actually an enterprise system in which we simulated a memory leak as a failure and how the system can deal with that autonomously without major disruption of the function. Security is some area that I've been active with recently. I'm working on the self-protection aspect of the system. I'm not dealing with security detection. Intrusion detection is not my area, but I'm using the output of intrusion detection system in order to, similar to what I use for fault diagnosis, to take the information from intrusion detection system to detect the early signs of abnormalities and attacks in the system, use this information to adapt the system to allow the system to save the data, isolate the compromised part, and maintain functionality at the maximum level. Again, it's an optimization problem, and it can be easily integrated with the performance management module so that I can have, in normal situation, the system will perform optimally, and in abnormal situation, whether it's fault, security attack, system can still adapt and maintain functionality as much as possible under these abnormal situations. There's a lot of preliminary work in this direction, but again, I want to have a generic form of integration between security management, failure management, and performance management. This is a simulated attack showing actually the system that we have already built some tool that does this using some optimization engine. And to capture actually this uncertainty of this, we use the Markov decision process to capture the uncertainty of the actions and the possibility that the attacker will take different scenarios to continue the attack with certain probability. We built actually a tool for that using domain-specific modeling language that can be used for all the way to simulate the attack. And actually here is a scenario that was simulated here was environment, including the attacker, going to a physical system, and we have a classifier, which is the IDS, and a controller that is used for selecting the action to take. Some action will be including to shut down some ports, shut down some communication links, move data to another server, increase the level of security at the firewall security, drop some packets, even shut down the whole system. And they simulated some attacks that come directly from this. This is the controller configuration. Using that, this is automatically generated from the simulation code that simulate the attack and show us how it works under different scenarios.
So is it like a if-then control? Like if
No,
this
no.
happens, then you will do this?
No, it's for this one, it's Markov decision process control in which you assign a reward function to each action, and you are trying to optimize the reward function.
Okay.
So we use a value iteration. It's a very basic algorithm for optimizing. So you get a plan of action from the current state that takes you from the current state all the way to the safe state in which the system is safe and free from the impact of the attack. So if you have different paths, then how the value iteration will go through all of these possibilities and compute the one with maximize the reward.
Like reinforcement learning?
Kind of, yeah, kind of. And part of it requires some learning in the beginning to get the correct attributes for this reward function and the probability associated with the transitions. Another area that I'm very interested to work on is the self-managing Internet of Things. Internet of Things is just growing rapidly and is gaining a lot of attention recently. It's the building blocks of everything that will come smart in the future. Talk about smart homes, smart cities, smart roads, smart grids. All of these have Internet of Things as the main building blocks. They are small sensors with computation capabilities, with good communication capabilities, and they are connected together with the system to gather data, analyze this data, and provide it to the user. So far, they are providing the data to another engine that try to take an action based on rule-based scenarios, different than situations. What we're trying to do is to use model-based techniques instead to make the integration more concrete and translate the problem into an actual optimization problem in which they are working on a common goal that is defined by the user and providing feedback. The user is providing feedback to the system in order to adapt to the demands of the system or the requirements, whenever it changed, and send that to the manager of the Internet of Things in sample to adapt the control problem accordingly. So my objective again is to build the overall structure, a tool for modeling, analysis, and design of generic form of Internet of Things that can be used in the future. One thing that I want to also move to here is the autonomous computing system. We have partnership with the University of Arizona, Texas Tech University, and they are going to welcome another center to add to that. We're trying to engage in research with industry. It's a good opportunity for industry collaborators to get actually partial funding for solving their problem from the government, NSF providing seed funds for that. And it's an excellent opportunity for them to have their problem solved, and also a very good opportunity for them to recruit students and train them for some of their domain operation domains. Some of the activities
they had no idea, some of the technologies were
test bed performance, security, and interoperability, big data analytics, and that all are focus problem for the cyber physical systems. Some of the past and present members that we worked with, and I'm sure because of the record that we built and reputation we have, will be a good chance to get them on board, or some of them on board, and also look for partners here in the state to join the center. Finally, I'm going to talk about teaching plans. Usually try to engage with the student in an interactive form, providing with the basic understanding, the formal foundation of the techniques, make sure that they are comprehending this base theory and get the knowledge to understand how it works and why it works in this way, and link that as much as possible to practical application. So I'm always linking theory with application. That I found this very useful for students to capture and be interested about the topic. Even when I talk about like formal methods, I always talk about it in a context of which is formal method is very theoretical subject, but putting that in a context of application like communication protocols or safety critical systems, make the students very interested on this, and rather than seeing it as an abstract form of knowledge. We also try to connect students with actual research problems. So part of the project that I gave are stemmed or connected to real applications that I work on in reality on some of the projects. And I get a lot of students working as a research undergraduate on that, or giving them some of the small problems that we're dealing with as part of the project part of the course. This is some of the classes that I can teach and already have experience in teaching. And as you can see, it's all pretty much within the context of system engineering. So I'm going to stop here because I'm pretty sure I exceeded my time, and take any questions.
Thank you very much.